Notes for section 3.5. Let's figure out how to find the derivatives of the trigonometric functions, known by their cute diminutive nickname, the trig functions. Derivative of trig functions. Haven't you been wondering? Somebody looked ahead and blurted out the other day, I know what the derivative of the sine function is. Well, let's take a look. If we wanted to, so if f of x is equal to sine x, we want to find f prime of x. Let's find the derivative. Well, anytime we come across a new function whose derivative we do not know, we go back to the definition. We say, well, let's see. I don't know what it is, so I'm going to go back and just write out definition. The derivative of a function is the limit as h approaches 0 of f of x plus h minus f of x all over h. Right? And where do we go from here? We can't like FOIL this out or anything because, and you know, certainly trig functions don't distribute over addition. But we do actually know an angle sum formula, sine angle sum. So remember good old days in pre-calculus when you learned that the sine of angle alpha plus beta, or a plus b, or whatever you want, x plus h in this case, is equal to the sine of the first one times the cosine of the second one plus the sine of the second one times the cosine of the first one. It was like the product rule in a way, don't you think? So let's apply that to here and see what happens. That's the limit as h approaches 0. Let's see, that'd be sine x is cosine h plus sine h cosine x minus sine x all over h. All right, see what we can do with that. I'm going to go ahead and split this up into some different pieces. So let's see. Let's take this piece. What's the limit? As h approaches 0. I'm going to go ahead and put this term and this term together over h. This is all totally legal manipulation here. Cosine h minus sine x. I'm just rearranging those terms and then doing the common denominator, sort of breaking it up into the two pieces. Oops, we got a 0 there. Limit as h approaches 0 of then this piece, sine h over h times cosine x. And that's also legal. You know that when you have something multiplying at the top of a fraction, you can bring that piece off to the side. In other words, exactly the way that like 3/2, for example, is equal to 1 times 3 over 2. It's the same as 1/2 times 3, right? That's what I'm doing there. All right. So you can pause for a second, make sure that all seems legitimate to you. I assure you it is. And then here, I'm going to factor that sine x. So what's the limit as h approaches 0? Factor off the sine x, and then I'm going to bring it out to the front, just like I pulled that cosine off there, times cosine h minus 1 h, and plus. Now, I want you to notice here, actually in both of these spots, this is the limit as h approaches 0. It doesn't say anything about what's happening to x's, so this, it really is not affected by the limit, the h going to 0. So it's really like we have this little limit, and then we're multiplying it by cosine x, like that's on the outside. Same with this. And hey, look, These are the two limits that we know from, is it section 2.5 maybe? The two trig limits. Remember the two trig limits that we learned way back when, last year? Or what the limit as x approaches 0, sine x over x is 1, and we also learned that the limit as x approaches 0, cosine x minus 1 over x is 0. Those are the two limits that we learned. We might have had this one the other way around, but of course negative 0 is still 0, so it doesn't matter. So look, this limit is 0, and this limit is 1. So this whole thing gets knocked out because we're multiplying by 0. And the answer is 1 times cosine. Look at that. The derivative of the sine function is the cosine function. That's pretty cool. And let's just go ahead and see if we can back that up with a little derivative sketching. So if we graphed, here's f of x equal to the sine function. Let's just sketch a little graph of that through one full period, like that. And then let's go ahead and make a sketch of the derivative of that. Well, let's see. First thing, when you're sketching derivatives, you try to find places where the slope is 0. So it looks like it's 0 right there and right there. So it's 0 and 0. And then here, the slope is positive, and it's as steep as it ever gets in the positive direction. And then here, it's as steep as it ever gets in the negative direction. And then it gets as steep. It's the exact same thing happening here as was happening here. So back up to that steepest. And lo and behold, that is the cosine function. Of course, it's only the cosine function if this, in fact, has exactly a slope of 1 and so on. But we just proved with the algebra and the limits on the preceding page that it is, in fact, the cosine function. And this just backs up our intuition. We might have, if I just had you sketch this and or draw the sine function and sketch the derivative, you might have guessed that the derivative was cosine. And you would be right. And just as an aside, this answers the question, why do we use radians? This is the answer. If you want, so the derivative of the sine function can be the cosine function. I don't know if you've seen this yet. This is like the operator form of the derivative. This is like the I'm actively taking the derivative of this guy form. It's like this is the y, so it's like d this dx. But if you want to like say I'm going to take the derivative of this thing, you can put a d dx in front, or d different letter if there's a different letter there. So anyway, this is just another way of saying the derivative of sine is cosine. We want that to be true. If you use degrees, this is not true. The derivative of the sine function is not equal to the cosine function. It's equal to some like a weird transformed version of it. But if you use radians, then the derivative of the sine function, the slope of the sine function, is precisely the cosine function. And if you don't use radians, that is not true. This is why we use radians. All right, let's just quickly go through. I guess we could, maybe I'll just extend down here. What if we then tried to draw the derivative of that? What's the second derivative? Or in other words, what's the derivative of the cosine function? So let's look at this now. This looks like it has a horizontal tangent there. It's steep as it ever gets negative. Then it's got another horizontal tangent, and then it gets steep positive, and then it's 0 again, so it looks like this. Well, what do you expect that is? Well, let's put that question on hold for a second. Let's see if we can prove it. So we're going to do here, if f of x is equal to the cosine function, let's find the derivative of that. I'll go a little bit faster this time. It's real similar to what we did for the sine function. So I have the limit, f prime of x is equal to the limit, as h approaches 0, of f of x plus h minus f of x all over h, cosine angle sum formula. Now, the cosine of x plus h, I'm not going to write it out off to the side. You could stop and think about it for a minute. It's this. Cosine x times cosine h minus sine x times sine h minus cosine x all over h. Now I'm going to split these up into separate little fractions again and do some factoring. I'm going to put these two terms together, and I'm going to go ahead and factor the cosine. Oh, that's right, that's too many steps at the same time. Never mind. I'm just going to put those two together. So that's cosine x times cosine h minus cosine x. Put those over their own version of the denominator. And then I have minus the limit as h approaches 0 of this term. You could put the minus sign on the inside and a plus there, however you want to deal with that. Doesn't really matter. Sine x times sine h over h. And again, the x is not happening. That's not affecting the x. So it's really just like whatever that limit is times that. And here I just need to do a little bit of factoring. I'm going to factor the cosine x off. Again, x isn't being affected, so that's just like a cosine x there. And I have cosine h minus 1 over h minus the limit as h approaches 0, sine x times sine h over h. And just like in the last problem, these are the two limits that we learned in Chapter 2. That's going to 0. This is going to 1. So this term is knocked out by the 0, and this is minus sine x. So sure enough, the derivative of the cosine function is negative sine. Now, what about the derivatives of tangent, cotangent, cosecant, and secant? Well, you can get the rest of them. Oops. Never mind that. I'll clean that up later. You can get the rest of them by using the product and quotient rules, actually just mainly the quotient rule, that we learned in section 3.3, right? So for example, if f of x is equal to tangent x, we want to find the derivative of that. So let's see. Well, tangent, all the other trig functions are defined in terms of sine and cosine. So I'm going to rewrite this and say, well, really we're talking about sine x over cosine x, right? So that's what I'm finding the derivative of, and that's a quotient. So the derivative of that is low d high, the derivative of sine is cosine, we just learned that, right? Minus high d low, the derivative of cosine is negative sine over low low. And we usually write that as cosine squared x. You could also write it as cosine x, like in a big set of parentheses, squared. All right, now let's clean that up. At the top we have cosine squared x, and then those two negatives, and do sine squared x over cosine squared x. Hey, cosine squared plus sine squared, that's like the one trig identity I remember, right? That's what you're saying to yourself. Maybe you remember the other ones. I hope so. But anyway, you know this one, right? Sine squared plus cosine squared, that's just 1, right? So you could leave it like that, but usually, typically, 1 over cosine is secant, right? So that's secant squared x. So what's the derivative of the tangent function? It's secant squared x. Go figure. Now, the rest of them, cotangent, secant, and cosecant, I could go through this exercise for you, but it's all just more quotient rule. So I'm not going to do that. I'll let you do that. Maybe it comes up in some of the homework problems. I'm going to make a table for you now of all of the trig functions and what their derivatives are. So if f of x is this, then the derivative is, if f of x is sine x, what's the derivative? Cosine x. If f of x is cosine x, then the derivative is negative sine x. If f of x is tangent x, then the derivative is secant squared x. Cotangent? If you were looking for a pattern here, I don't know, maybe, what would you guess? What would you guess? Well, did you guess negative cosecant squared? How about the derivative of the secant function? The derivative of the secant function is secant x times tangent x. And now that you know that one, maybe you could take a guess looking at the pattern again. Then just pause it for a minute and see if you can look at that pattern and see what, if you had to take a guess. Did you pause? Give me another chance. It's negative cosecant x times cotangent x. All right, now, you need to know these. These need to be memorized. You can, if you only know these two, it's possible to get the rest of them by using the quotient rule. But you're going to refer to and use these enough, often enough, and have to do it speedily enough that I really don't think it's a good idea to only know these two. Okay? I'll show you a couple of tricks. Did you notice that everything that starts with co has a negative derivative? That helps a little bit. Sine goes to cosine, cosine goes to negative sine, tangent goes to secant squared, cotangent goes to negative cosecant squared. And then once you get into the into these ones, the cos go with the cos, right? Tangent goes with secant squared, cotangent goes with cosecant squared, secant goes with secant and tangent, and cosecant goes with cosecant and cotangent. So there are other patterns. It's not like there are like 6 totally isolated, unrelated pieces of information that you have to remember. They really are, I think you can kind of compress that information a little bit better and understand some patterns and relationships there. Right. One last real quick thing that I'll point out to you is that if you take successive derivatives of the sine function, so if you have f of x is equal to sine x, and then what if you wanted to take the derivative, and then the second derivative, and then the third derivative, and then remember how to write the fourth derivative? We get tired of doing that, so we do this, and then the fifth derivative, and the sixth derivative, and all right, fine, you get the idea, right? So what are they if we just go through? Is there a pattern? The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine x, well, it's just negative whatever the derivative of the sine function is. That would be like negative cosine x. And then the derivative of negative cosine would be positive sine x. And then, oh look, we're back to the beginning of the cycle, right? So then it just repeats over and over again. So unlike with, like for example, what's the derivative of x to the third? It's 3x squared. And then you do it again, you get 6x. You do it again, you get 6. You do it again, you get 0, and then it's forever 0 after that. This just spins around in circles, right? It just keeps going and going. Is there anything else you've ever seen that followed a pattern like this, like a 4 cycle like this? Can you think of anything else? Well, I'm not going to tell you what it is. I bet you can think of something else. And this is the first suggestion of a very deep and profound relationship between the trigonometric functions and the other thing that you thought maybe this kind of reminded you of. Unfortunately, we won't really be able to establish that relationship until much later in the year. Do you want to see what I spilled all over the floor? Those things. I'm going to go clean them up now.